So standard deviation, they both have the same mean, so that means the middle of the data is the same on both of them. Alright? Standard deviation tells us the spread. So one of them has a standard deviation of 16 and the other one 24. Which one do you think has a standard deviation of 16? How come B? It's not as spread out. So B is the one with the standard deviation of 16. And then 24, if you look at the other, if you look at A, you see how it's more spread out? More spread across, it's going to have a bigger standard deviation. So the bigger the standard deviation, the more spread out the data is. The smaller the standard deviation is, the closer together the data is. Alright, so if we had something like this, if we had something that looks like this, let's try to pin it off. Is that going to have a big or a small standard deviation? Small, because it's all close together. If we have something that's like this, that's going to have a big standard deviation because it's more spread out. 22, is 22 the same kind of setup?
Mm-hmm.
Yeah. So which one has the big standard deviation? B. Which one has the smaller standard deviation? A. Because it's all compact and they're all real close together.
Can we do 5?
Number 5. Construct a sample data set which n equals 7, x bar equals 9, and s equals 0. So the standard deviation is 0. If the standard deviation is 0, what's that telling you? They're all the same, right? All the numbers are the same. So how many numbers are we going to have? 7. What they tell us did they tell us the mean? 9, 8, which one is it? 9. And they're all the same, so 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7 numbers. I didn't really need that last comma, did I? What's this number going to be?
9.
What's this number going to be? That's our data set. The ones that are hard, and I don't know if I put any of them on here because I hate doing them. The ones that are hard are when they don't give you something like where they're all the same, and they want you to.
So
6
6
is one of them.
Yeah.
Shouldn't have opened up my mouth. Construct a population where n is 6, the mean is 5, and the standard deviation is 2. So, sorry, this is a population. So n equals 6, mean is 5, they said, and the standard deviation, it's sigma, is 2. So we want to set, well, we got how many numbers?
6.
2, 3, 4, 5, 6. We want the mean to be what? 5. And we want the standard deviation to be 2. No real easy way to do this. First of all, can every number be 5 like it was up here in this one? No, so we want them to be spread out a little bit. But we want 5 to be where? That's the mean. Where's it going to be? In the middle here. So maybe I put a couple of 5s in there.
You can do 3, 3, 3, and then 7. 7.
But you don't want any 5s. You want 3 3s and 3 7s.
3 3s and 3 7s. Is that what we want? This one, so this one won't work? I don't know, let's try this one. Grab your,
Divided by 6.
grab your calculator, could we just plug it in there, or do we wanna do it out longhand?
That works, so
I don't know. It works, what's our mean gonna be here?
5.
See, we got 20, 30, divided by 6, the mean is 5, so that works. We got 6 numbers,
The deviation at two.
but the standard deviation we need to be 2. Is the standard deviation gonna be 2 if we have this?
No.
It's not? What is the standard deviation?
1.63.
What's that tell us? The standard deviation is 1.63. We need our data to do what? Is it gonna be closer together or more spread out? More spread out because our standard deviation is bigger than that, right? So let's try a different list. You said 3, 3, 3, and 7, 7, 7. Is
Yeah.
that what you wanna try?
Yeah.
We add all those together, that gives us 30. 30 divided by 6 is 5. So our mean works. Is the standard deviation 2 this time?
Yeah.
Yeah.
Now, is that the only list that's gonna work? There's probably a whole bunch of them that work, but if that's one of them, then that's all they asked you for was one of them, then we probably stop right there. Other questions? Anywhere out in the real world where you're gonna have to come up with a list where the mean is this and the standard deviation is something special? Probably not. It's always gonna be going the other way around, right? Where you have your list, you collect your list from somewhere and then you find those things. Other questions? Twenty-four. An internet site compares the strokes per round for 2 professional golfers. Which golfer is more consistent? Player A with a mean, let me write this down. So this is player A, they have a mean of 71.5. And a standard deviation of 2.3. This problem should really take y'all about 30 seconds to do, and I'm taking longer to just read it than it actually should take. Player B has a mean of 70.1. And a standard deviation of 1.2. They want to know which player is the most consistent. What would we look at to figure out who's the most consistent?
The standard deviation.
Alright, so if we're looking at what we just had a minute ago when I had this and I put this on here and we said this one has the smaller standard deviation, that means all the numbers are really, really close together there. When we're looking at the golfers, that's what we're looking at is the most consistent one. We mean which golfer shoots about the same just every single time. Well, so which golfer would it be? Because the standard deviation is 1.2. Which one's the better golfer? Which one has the better scores? B also. I thought maybe I'd trick somebody with the golf thing being the lowest score is better. Couldn't fool them, could I, did? Other questions? Other questions? understands it. We should just take the test over today.
If that's what we gotta do.
Oh,
Yeah.
that's
We
it.
just failed it.
Yeah, I like Sean.
Again.
Yeah, we good?
Sean's my favorite. Yeah, that's all right, what we're gonna cover today, measures of position. So we've talked about, we had this set of data. I'm just gonna draw the curve. We had this set of data. We talked about the stuff that was in the middle, measures of central tendency. Last time we talked about measures of variation, telling us how the data moves in and out from that center. Now we're going to talk about measures of position. So we're going to be looking at certain positions in the data. Measures of position. Don't write any of this down. We're going to learn how to find the first, second, and third quartiles. Have you ever heard the quartiles? Yeah, that was on your calculator, right? Interquartile range, that's not on your calculator. I don't think. Seems like last year we learned that it was on the calculator somewhere. I have to try to figure that out again. So the interquartile range, we're going to learn how to do that. We're going to learn to use a box and whisker plot. And we're going to deal with fractiles, which of those fractiles we're going to deal with. Percentiles is the main one. And then something that we're going to do all year long, we're going to find z-scores. Z-scores and t-scores we're going to talk about throughout the year, and I'll explain what they are when we get to them here in a minute. This is just review. Scores that are 2 standard deviations away from the mean, what do we know about them? They're unusual. If they're more than 3 standard deviations away from the mean, then they are very unusual. All right, a fractile. I'll put all these up here. My pen doesn't want to work all day. A fractile is just taking the set of data and dividing it up. So quartiles, all the stuff that we talk about, or most of the stuff that we talk about today, are fractiles. Fractiles like the big group, and then quartiles is one way of splitting it up. Percentiles is another way of splitting it up, and so on and so on. Quartiles and percentiles are the two that we're going to deal with mostly. With quartiles, if I have, let's say that's a number line. My lowest number in my set of data, whatever it is here. My highest one is here. first of all, what's quart mean? 4. So we're splitting it up into quarters, 4 parts, all right? How many times, if this was a board, and I was gonna cut this board, and I had to cut it so that 4 of us could share it, how many times would I have to cut it? 3. So how many quartiles are there gonna be? 3. So I'm gonna cut it something like that, all right? This is quartile 1, quartile 2, quartile 3. Now, what those tell you when you're looking at quartiles is that 25% of the data falls in this range, 25% of the data falls in this range, 25% of the data falls in that range, and 25% falls in that range. That's all quartiles are. Quartile 2 is also the median. So if we put all the numbers in order, list them all in order, that middle number is the same as quartile 2. So that's sort of important to remember that, because sometimes they'll ask you for the median, sometimes they'll ask you for quartile 2, you need to remember that they're the same thing. Nothing hard about finding quartiles, nothing hard about splitting it up. You just gotta look at the data, and what you're gonna do, you're gonna find the median first. So you might wanna write that down. You're gonna find this first. Then once you have the data split up into 50% on one side and 50% on the other side, you're gonna find the median of this side, and that's gonna be where quartile 1 is. Then you're gonna find the median of this side, and that's where quartile 3 is. So you just find the median 3 times. You find the median of the big set of data, then you find the median of each of the 2 halves of the sets. Remember, when you're finding median, you find either the middle number, or if there's not a middle number, you take the 2 middle ones, and what do you do with them? Add them up and divide by 2. Add, then divide by 2. So if there's not a middle one, you just add them together and divide it by 2. Number of nuclear power plants in the top 15 nuclear power producing countries in the world are listed. Find the first, second, and third quartiles of the set of data. What's the first thing we're going to do with this list? You got to put it in order. So let's go through and just tell me, and I'll write them down here.
6, 7, 8.
Hold on, let me mark them out so that we don't get confused. 6, 7, 8. All right.
10, 11.
All right.
15.
15.
Yeah. 17, 18.
No, I didn't mean to put a comma there. Don't ignore that.
20 or 19.
19.
20.
Wait,
There's another 18.
It's 2
Oh, there's
18.
2 18. Oh.
We need 18. That's an 18. Everybody can remember that, right? 19, 20.
31. 54. 59. And 1 4.
54, 59. Did we get them all? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Is that what we said, 15? So if there's 15 numbers, how are we gonna find the middle? What's half of 15? 7.5. So what I do is, and you can do this 1, 1, 2, 2, if that's what you do to find it, that's fine, I don't care. But I just divide it 7.5, that means 7, so I count over 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So what's quartile 1? 18. Or quartile 2, not quartile 1, sorry. So quartile 2 is 18. Now to find quartile 1, we're we're looking at 18 right here, that's our middle number. We look at just the numbers down here, how many numbers are on this end? 7. So, how many numbers would I have to be able to be right in the middle? So, 1, 1, 2, 2, 3, 3, 4, so what's quartile 1? Then you do the same thing on the other side, how many numbers are over here? 7, so find quartile 3, 2, 3, 4, what's that? 31. Those are our 3 quartiles. So all we're saying there is if we split the numbers up here, we split them up here, and we split them up here, what percentage of the numbers should be over here? 25%. So we got 3, somebody help me out with your calculator. 3 out of how many? 15. So what's 3 divided by 15? 20%? How many is in here? 3, so that'd be 20%, 20%, 20%. Now what we're not including is those numbers, and they would have to fall in there also, and that's where the 25 would come in. But those are our quartiles. Nothing hard about finding quartiles. Split the data up into 4 parts. Usually when you're dealing with the quartiles, if we're at quartile 1 here, you're looking at that point, or that number, down. This number, down. This number, down. So that's what we came up with. About 1/4 of the countries have 10 or less. So 25% have 10 or less. About 1/2 have 18 or less. And about 3/4 have 31 or less. So 75% of all the countries in the world have 31 or less nuclear power plants. What's wrong with this set of data? Not really wrong, but what's sort of messing up this set of data? That 104 is quite a ways out there, isn't it? So we're gonna learn something about that too here in a minute. Oh, if you type this into your calculator, there's something on your calculator that'll put it in order for you, and I can't remember what it is. So you wouldn't have to set and put it in order. Anybody find it on there? Go to, on your calculators, look at where it starts off with edit. So go to stat. Sort. That's what it says, isn't it? If you put the list in there, just put it in there and then hit sort, and it'll say ascending or descending, I think, right?
There's a sort A and a sort B.
Oh, is there? So,
It's the sort A, and then you put the list in there, it says done.
and then if you go back to the list, it'll have it in order. It'll have all the numbers either from lowest to highest or highest to lowest. Ascending is lowest to highest, descending is highest to lowest.
So, if they wanted us to list all of them, would we count 10 as a part of
The lower
quartile
one.
one? Okay.
Yeah, so you're going from, if this is quartile 1,
Yeah.
you're going from here down. If this is quartile 2, you're going from here down.
I'll make sure.
And then when we get up here, so that's where if we did, somebody help me out, what's 4 divided by 15? What is it? 26. So that's really close to 25%, and that's what we think it should be. And then from here down, there's 4 more. The only one that sort of gets messed up is that top one up there. There's only 3 in it, so it's only 20%, but that's because we put extra percentages in the others. Now, a lot of times with quartiles, it won't be like, right on 10. So if the quartile is 10.5, because we had to add these two together and divide by 2, then you can sort of more easily tell which numbers fall in which quartile. But the quartile goes with everything below it. The IQR, the interquartile range, is the difference between the third quartile and the first quartile. So all you're going to do to find the IQR is subtract quartile 3 minus quartile 1. What percentage should fall in these two, between 3 and 1? 50%. So that's what's special about it. It's the interquartile range is, the interquartile range is 50% of all the data. So you have 50% right here in the middle, then on this end you got 25%, on this end you got 25%. Interquartile range is easy to find, nothing really hard about it. Just find quartile 3, quartile 1, subtract the 2. And we'll talk about what we use it for as we go throughout the year. Easy stuff, Gage. Pretty easy. Gage, I've been pretty impressed with you this year even.
Me too.
Find the interquartile range of our set of data. Which two numbers are we going to use? 31 and 10. What's 31 minus 10? 21. That's the interquartile range. The number of power plants in the middle portion of the data set vary by at most 21. Again, that's 50% of the data. Using the IQR, this is where one of the places where we're going to use the interquartile range. Using the IQR to find outliers. Write these two down. Those are two formulas. And those formulas tell us where outliers fall. So we can tell if I was right or not about that 104, see if it's an outlier. We'll do that here in a second. So if we want to check and see if any of these are outliers, what was quartile 1? 10 minus 1.5 times what was our IQR? 21. Type all that right into your calculator. You can type it in with parentheses and all, and it'll do all the work for you. Anybody else get that? Do the same thing down here. What's quartile 3? 31 plus 1.5 times 21 again.
62.5.
Now what we're looking at here, when we find these two numbers, we're going to go back to our data. Negative 21.5 would be way down here somewhere. 62.5 would be right here somewhere. Anything that falls outside those two can be considered an outlier. Do we have anything on this end? No, because you can't have negative, well, I shouldn't say that because, what's the country over there right now?
Russia.
No, the other one that they're in. Ukraine might have some negative nuclear power plants right at the moment. Russia bombing them. That's real smart, isn't it? So if Riley lives right next to you and he's got a nuclear power plant? Do you wanna bomb it
I
and
see
blow it
the
up
problem.
and have
That's what they wanna do.
that, have that nuclear stuff spread all over? That's really intelligent, isn't it?
Well, we're not trying to take over the country.
That's what happens when we run.
So, nothing down this way, but what do we know about the 104?
Outlier.
It's an outlier
Get
because
that thing
it's
outta here.
farther out that way. Sometimes if we find out there's an outlier, we'll leave it off the data, then redo everything without it in there. Other times you want it in there, because it might make a difference. All right, a box and whisker plot. Let's see here. Main thing with the box and whisker plot. Don't write these two. Write this. 5-number summary. Very important. And these are the 5 numbers. 1, 2, 3, 4, and 5. And that's how you're going to create a box and whisker plot with those 5 different numbers. Anybody ever seen a box and whisker plot? Is that a yes, Zoe? So the 5-number summary, just those 5 numbers, none of them really hard to find. Minimum, what's that tell you to find? Lowest number. Maximum, what's that tell you to find? The biggest number. Then the 3 quartiles. So to make a box and whisker plot, we're going to find those 5 numbers. That's what we're going to do. This is just telling you how to do it. I'm going to show you how to do it. And then... Alright, so when you do it, and hopefully you'll be able to memorize this, so you don't have to write all this down. It's so silly. Find the 5 numbers, construct the number line, plot the 5 numbers on that number line, draw a box between quartile 1 and quartile 3, so that interquartile range. And then connect the box to the minimum entry and the maximum entry with little whiskers. So if we do one here, they already did it for us. Let's go back to ours. I'll just do it over here on the side. So I'm going to draw myself a little line, number line here. On my number line. What was my quartile 2? What was it? Nobody remembers?
18.
18. What was quartile 3? 10. Now, your number line shouldn't, mine looks like they're the same, and this shouldn't be the same. 10 should be closer to 18 than 31 is, right? What was the lowest number? So I have my, let me do it a better way, otherwise Alexa's gonna be upset with me. I have a number line. We're going from the lowest number of 6, so we'll start at 4. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I ain't gonna be able to make it, am I? We got big numbers. Let's start at 5. We'll go 5, I think these, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 95. What was the highest one we had? So that should get it right. So I have my number line here. What I usually do is above it, what was my lowest number?
6.
So I put a dot where 6 is. What was my highest number? So I put a a dot where that is. Then you got your 3 quartiles. On your 3 quartiles, you're just gonna do this. One of them was 10, right?
Yeah.
So I put a bar where 10 is. The other one was 21, is that right? 31. 31, that would be somewhere about in here. I put a bar. And the other one was 18. That's somewhere about in here. Put a bar right there. So I have these 3 bars and these 2 dots. I make the bars into a box. And then I just connect the box to the max and the min. What percentage of the data is in this range and inside this box? 50% in the whole thing, right? What part's in each part of the box? 25%. What part of the data is on this little whisker right here? 25%. What part's on this big whisker over here? 25%. Again, you notice how it looks all stretched out and stuff? How come it looks all stretched out?
Numbers get bigger, more spread out.
You got the outlier out here, right? So on 104 out here, what you might do, put an asterisk on 104, that means you have an outlier there. What's the highest number without the 104? So what was it? It was like 60,
Something.
62 or something like that?
59.
59 was the highest? So about there. That might be a little better box than whisker plot. What part falls on this whisker?
25.
25%, there's 25% in this little part, 25% in that little part. What's this part in here inside the box called again?
IQR.
The IQR, the interquartile range. Some things here, quartiles. On this, these are different fractiles. Fractiles, again, are the ways that we can split up all of them. Deciles, we're probably not going to use deciles. But deciles is when you split something up into 10 parts. Quartiles, you split it up into 4 parts. Percentiles we are going to use. I would write this right here down. Percentiles, you're splitting something up into 100 parts. A whole bunch of you, as you apply to schools and stuff, they're going to look at your percentile ranking. They're going to look at, out of 100, where do you rank in that? Something else you might want to write down with it is I wrote it over there, but anytime you see this, let's not do that. P and then a little subscript with a number, that is read 18th percentile. 18th percentile. If your score is P18 like that, then what that means is that you scored higher than 18% of all others, whoever was doing whatever you're doing. So you scored higher than 18% of them. So what's that mean as far as how many people scored higher than you? 82% scored higher than you, all right? So when you read that, that's how that's read, and that's what it stands for, and that's what it means. So if you're looking at something and it says your percentile rank 38, that means you scored higher than 38 people doing whatever it is that you're doing. Or 38% of the people doing whatever it is that you're doing. That's how percentiles work. So when we take this first symbols test here in a few days, and you see this on there, what definition are you going to give me of that? It's the 52nd percentile. If you scored in the 52nd percentile, did you score better than more people or worse than more people? Better. Because you're in the top 50, the upper half. Interpreting using percentiles. So if they give you a percentile, this chart here is in percentiles. What kind of chart is this again, Phoenix?
The O guy?
I think it is, right? So if we're looking at this and they want to know, let's see, what's it ask us here? What test score represents the 62nd percentile? So I just go up here to 62nd, somewhere about in there. Everybody agree that's about right? And I come over, somewhere about there.
600 each pushing
About what is that, Doug? Is that real
About
crooked?
600?
Is that pretty good? About how much? 1,500, a little more than 1,500 maybe, 62nd percentile. What's this telling us? 62nd percentile. You scored better than 62% of everybody else who did, took the ACT or SAT. See if they came up with the same thing that we did. Oops, I went too far. My line must have been way crooked. Why didn't you tell me that? Can't tell up here. Percentiles used to compare scores. Above the 95th percentile is considered unusually high. So when Brendan took the SAT, he scored in the 95th percentile. He was considered to be unusually high. Below the 5th percentile is considered unusually low. Phoenix started to say something stupid, didn't he? Call yourself. Thank you, Phoenix, for catching yourself. 78th percentile means that that piece of data is higher than 78% of all the other data entries. Bad thing is now, most of you probably already done with the ACT and SAT and all that stuff, right? You've already taken it and forgot all about it. But when they send you back your information and stuff now, if you got back the information and they say you scored in the 75th percentile, now you would know what it means, right? Whereas before you probably got it and you read it and you went, okay. You didn't have a clue what it meant.
16, 18 ACT scores.
What?
I have an inability to read and write, so I average a 16 to a 17.
You're in the what?
Like the 90.
Exactly, I can't read or write.
Wait. So, and that's another thing with babies. If you have a little brother or sister or something, you go to the doctor, and they'll have a little graph that looks like this, and they'll put a little asterisk on there, and a little asterisk on there, and one's for weight and one's for height. And they'll tell you, hey, your baby is in the 92nd percentile. 92nd percentile as far as weight goes. But as far as height goes, they're in the 22nd percentile. So they tell you that stuff, and then that helps them to decide, that helps them decide what's going on with the baby, whether, you know, there needs to
So
be
what are you at?
fed more, fed
Are
less.
you buying height too?
Like this. I'm like 90. Wait, does that mean I'm fat? I'm there, they say.
Yeah, I got the 99 percentile.
Makes me feel so fat when I see it. It's like, that's a big number.
A standard score, a Z-score, very, very, very important. So Caden, you back with us?
Yeah.
How was the nap? I took one the first day.
Yeah, like, is it the 30%?
I gotta keep myself away from the wall when I'm taking a nap.
A Z-score, a standard score, represents the number of standard deviations a given value X falls from the mean. We're going to learn how to change any of the scores into a Z-score. That way we can compare different things. So, like if you took the SAT and you took the ACT, well, you can't compare a 1200 to a 22 or whatever. It just doesn't work. But if we change them into Z-scores, then we can compare. All right? Or if you're looking at your English test compared to your biology test, we can compare those two, even though they're not the same kind of test, if we use standard scores or Z-scores. This is the formula to find a Z-score or to change a number into a Z-score. Now with this one, it looks like that I'm using what? A population or a sample? Population. So this is if we're dealing with a population, which it doesn't really make a whole lot of difference. Anybody tell me what's the formula going to be for a sample? X minus X bar over S. So that's for a sample, the other one's for a population. Both the same thing, you just got to know the mean and the standard deviation. X is whatever score you're looking at. So Phoenix's ACT score is a 23, and that's the one we're looking at. Then that's what we put on there. Take that minus the mean. Make sure you hit equals when you do this. You plug it into your calculator, because if you don't, then it's going to give you the wrong answer. Then you divide by the standard deviation. Now the bad thing with changing everything to a Z-score is you have to know what? The mean and the standard deviation. So you have to find them first. 2009, Heath Ledger won the Oscar for Best Supporting Actor at age 29 for his role in the movie The Dark Knight. Wasn't that the Joker or something?
Yeah, then he overdosed.
Yeah, they died right soon after that.
Yep.
So he won Best Supporting Actor at age 29. Penelope Cruz won the Oscar for Best Supporting Actress at age 34 for her role in Vicky Cristina Barcelona. A movie that I'm sure that
You watched
Phoenix
that?
watched many, many times.
I gotta look that up. See that.
Put your phone
I'm
away.
looking at movies.
No, I'm going to take it.
Throw it at the wall and we'll take it.
Supporting actor winners, I'm sorry, the mean age for all Best Supporting Actor winners is 49.5 with a standard deviation of 13.8. The mean age for all Best Supporting Actress winners is 39.9 with a standard deviation of 14.0. Find the z-score that corresponds to each of their ages, and then compare the results. So before I change this slide, can we really compare and say, okay, Keith was a whole lot better than Penelope just because he's a lot younger, he's 5 years younger there? No, because we don't know how it works, and that's, we can compare them if we change them into the same kind of numbers. Alright? So what we want to do here for Heath, to find his z-score. What was his age? So 29 minus, what was the mean for actors? 49.5. What was the standard deviation for actors? 13.8. Grab your calculator and help me out and do that math there.
You gotta click enter before you divide it. So it's
Or
negative.
put the top in parentheses.
So make sure you got to tell your calculator, do this part first, then divide it. Negative 1.48. Anybody else get that? 1.49. Now, before I go on to Penelope's, remember we're looking on like a normal curve here on a number line. The middle number here is 49.5. We got 3 standard deviations above, 3 standard deviations below. We're saying that we are where? About 1.5 standard deviations below. So we're somewhere about right in there. All right, does that make sense so far? Now for Penelope, what was her age? 34 minus
39.9.
So if I'm looking at my number line here, right in the middle, I got 39.9. That's our mean. 3 standard deviations above, 3 standard deviations below. Where does she fall at? Tell me when to stop. About there? Which one do you think, and it says explain, this one I would want you to explain on. Which one do you think was more impressive, Heath's or Penelope's? How come? Alright, he's farther away from the mean. The farther away you get from the mean, remember the more unusual things are. So it was more unusual that he wanted at his age than Penelope wanted at her age. The other thing I want to show you here, and you might want to write this in your notes somewhere, as I'm drawing this, you're going to have to know this. You might want to draw something like this number line. The mean's right here. Then we got 3 standard deviations above, 3 standard deviations below. Instead of using the mean and then subtracting off these crazy numbers like 13.8 and all, whatever they are all the time, or adding 13.8, when we change to z-scores, this is what's going to happen. The mean is always going to be 0. Then our numbers here are just going to be 1, 2, 3, and what's on the other side? So when we change into z-scores, then our graph looks like this instead of having 49.5 and Then over here would be like 62.3 and so on and so on. Instead of having those scores, these are called raw scores. If we change it into z-scores, then our graph just looks like this now. 0, 1, 2, 3, 0, -1, -2, -3. And then we can tell that Heath was about -1.5. That would fall right about there. So when we change it all into z-scores, then we can look at it a little easier. And we'll do that stuff as the year goes along quite a bit. So Heath, we said -1.49, -4.2, and then they'll probably explain it to us. Both scores are between -2, so neither score would be considered really unusual. But if we're comparing the two, Heath was probably a little better because he was a little bit younger, a little farther away from the mean. That's your assignment.
Oh, why don't you put it on the back of that?
I put it on the back of the notes.
I do that too.